Welcome. In this video, we are going to take a look at problem 4. It is from chapter 29 of College Physics 2E by OpenStax. We need to find the longest wavelength radiation that can eject a photoelectron from silver. And we know the binding energy, and then we need to figure out if it's in the visible range. Okay, so let's write down what we know. We know the binding energy, we'll call it BE, is 4.73 electron volts. And we are looking for the longest wavelength. So that will correspond to the lowest frequency. The lowest frequency happens when KE, kinetic energy, is 0. Okay. So we can start with KE is equal to HF minus BE. And so we set the kinetic energy to 0. We get HF minus BE. And so HF is equal to binding energy BE. We also know that C is lambda times F. So the frequency is the speed of light divided by the wavelength. So we can make that substitution. We get hc over lambda is equal to the binding energy. So lambda times the binding energy is equal to Planck's constant times the speed of light. And so lambda is hc over BE. So making the substitutions, Planck's constant H is 6.626 times 10 to the minus 34 joules times seconds. Speed of light C is 3 times 10 to the 8 meters per second. We're dividing by the binding energy, which is 4.73 electron volts. We need to convert this to joules. There are 1.60 times 10 to the minus 19 joules for every electron volt. I did this calculation and I found a wavelength of 2.63 times 10 to the minus 7 meters. And so that is 263 nanometers. Okay, so that's the wavelength. That's the longest wavelength. Now the visible range is around 380 to 750 nanometers. So this is not in the visible range. The UV or ultraviolet range is from 100 to 400 nanometers. And so we can say this wavelength is in the UV range. So not in the visible, it is in the ultraviolet. I hope you found that helpful. Let me know in the comments section if you have any questions. Thank you for watching, and I'll see you in the next one.